Good morning, ladies and gentlemen. As we gather here today, I am pleased to note that we have reached more than halfway of our one-week offline faculty development program titled as Solar Effect on Climate Dynamics and Renewable Energy towards Sustainable Solutions, proudly sponsored by the AICT Training and Learning Academy. I am Dr. Momita Shahu, the co-coordinator of this FDP program, and it gives me immense pleasure to welcome you all to the 5th day of this enriching program scheduled from November 18 to 23rd, 2024. This program is organized by the Applied Electronics and Instrumentation Engineering at Haldia Institute of Technology. Today we are privileged to have with us an esteemed speaker, Professor Dr. Shankar Narayan Patro, a distinguished professor at the Department of Instrumentation and Electronics Engineering, Jadavpur University, Kolkata, whose contributions to the field of instrumentation, electronics and sustainable technologies have been truly commendable. So before we proceed, let us welcome our speaker onto the dais with a round of applause. Thank you, sir. Now I warmly invite our head of the department, Professor Dr. Uday Maji, to the dais. Now I request Mr. Devdapta Ghosh, Associate Professor of AI Department, to the dais. Finally, I welcome the coordinator of this program, Dr. Soumya Roy, Associate Professor of AI Department, to the dais. We are deeply honored to have such a distinguished dignitaries on this dais today. Now let honor the dynamic personality on the dais with felicitation ceremony. Now to honor our esteemed speaker, Professor Patro, I request Professor Uday Maji, head of the Department of AI Department, to present a plant as a symbol of our deep respect and appreciation. Thank you, sir, for the warm gesture. Now, I would like to symbolize our commitment to growth, sustainability and knowledge with the watering of the plant ceremony. This plant represents the growth of ideas, knowledge and initiatives towards a sustainable future, which is a theme of our program also. I would like to respectfully invite our esteemed speaker, HOD sir, coordinator and NHU sir for this FDP program to come forward and water the plant. Thank you for this wonderful start of our event today. We are honored to welcome Professor Dr. Shankar Narayan Patro as a distinguished speaker for today's session. Professor Patro is a prominent figure in the field of instrumentation and electronics engineering, currently serving at Jadavpur University, India. Professor Patro has an impressive educational background, holding a BSc in Physics, a BTech and an MTech in Instrumentation and Electronics Engineering from Jadavpur University, as well as a PhD in Mechanical Engineering from the same institute. Professor Patro has served as the head of the Department of Instrumentation and Electronics Engineering from 2019 to 22 and has also led the Department of Instrumentation Science. In addition to these academic responsibilities, Professor Patro is the Honorary Advisor of the Instrumentation Section at Flensor Technologies Private Limited. His research expertise spans astronomical data processing, AI-driven image processing, and sensor and instrumentation design. His contributions to discrete time signal processing, fractal dimension analysis and stochastic modeling, particularly in astrophysics and solar data applications, have gained widespread recognition. Professor Patro has made significant contributions to science and technology with around 100 publications in reputed journals, conference, books and book chapters. With numerous publications in prestigious journals like Astrophysics and Space Science and Solar Physics, Professor Patro's work is highly cited, reflecting his significant impact on both theoretical and applied research. He also holds a patent for a smart cosine error optimized sensor network-based solar irradiance measurement system, showcasing his innovative contribution to the field. Beyond his academic achievements, he is a dedicated mentor and teacher, inspiring students and researchers to excel in their careers. We are privileged to have Professor Patro with us today to share his insights and expertise on the topics basic instruments and data analysis techniques for solar astronomy. So without further delay, let us welcome Professor Patro to lead this session. So sir, stage is yours.
The first part, solar effect on climate dynamics, probably is quite related to the geophysics and solar physics. Whereas in renewable energy is a keen research area of advanced engineering, material science. But probably we are well known about this part. But what I am going to say about, particularly today, we are going to talk about some instruments. Okay, what I am going to say today is particularly a little bit different. It's not a conventional instrument we studied in our department, like we are probably most of us from instrumentation background and electronics background. So whatever we studied is a little bit different in that sense of applications, not the sense of its construction. My topic right now today is a basic instrument and data analysis for solar astronomy. So when we are going to talk about that solar astronomy and its instrument, definitely we have to start from the science. And science means it's not an understanding of solar physics or the universe. Actually, it's unlocking its secrets. Unlocking its secrets in the dynamics of the solar physics. Because we know about the process parameter, we know the process as well as we know how the parameter will be measured, because we can feel, we can touch, we can install that process in our basically industrial process, whatever we know. But when we are talking about the solar physics, the process is not known to us. So whatever we are going to discuss, basically depending on some analytical instruments. Okay, let me start with my slides. When we are talking about some stellar physics or solar physics that actually come out from stellar physics, so we have to say about Subramaniam Chandrasekhar. He is an Indian pioneer in the field, and he got Nobel in 1982 around, and the only person who got Nobel on theoretical physics. Actually, he has immense contribution in theoretical physics. For what? Lot of things I have been told. So he awarded these Nobels, and he actually given some parameters to explain the stellar physics or stellar structure. One of them is the Chandrasekhar limit. This one is popular, and Chandrasekhar limit is 1.44 of solar mass. So whenever we are going to define a star in astronomy, we have to express its weight or its mass with respect to a unit solar limits or Chandrasekhar limits. Now, let's enter in our world of astronomy first. This is the picture of Milky Way, where the astronomers are constantly learning new facts as space exploration and technology evolves. To make the sense of these new things, it's important to know its secrets, as I said earlier. So when we are talking about some stellar bodies, definitely we have to know how the stars are created. Stars actually a combination of helium hydrogen, mostly helium hydrogen and a gaseous thing. And definitely there will be some plasma stage of the materials, not fully gaseous form in that case. Including our own suns, the Milky Way galaxy and the million of galaxies in the universe will be find. Here, the astronomy, the study even maybe most ancient of the science. And we are very much proud that our Indian ancient history, if we study, we will find that there is a very, huge proof that we are very much aware of astronomy. I would like to say one name here. I'll come to that slide later on Japanese scientist who actually who actually did the research on ancient astronomical instruments that given by our Indian history. Before this one, let us start with some expression how the stars are created. So star develop a giant slowly rotating cloud. It's made up almost entirely hydrogen helium that I said. Due to its own gravity pulls the cloud behind the polar unwind inwards, and as it sinks, it spins more and more quickly, with the outer parts becoming disks, while the innermost part becomes roughly spherical form. So here, these lines are not very much clear. Here a magnetic pool for over the look. This disc has been formed, and then after what happened, the discs which actually form of a plasma as well as stage of dust. The dust are even cooled by the star, and that magnetic line is not prominent here, but now it is prominent. Okay, that due to huge temperature at the center, it's like a 1 million degrees centigrade. The fusion happens when hydrogen helium fusion happens, and for what? The huge energy come out from the center of the star, which nearly 1 gram of mass converted into energy would be equal to the expression roughly 22,000 tons of TNT. After hydrogen fusion starts, the result is a T2 stars, the variable star that fluctuates in brightness, and the star continues to last for roughly 10 million years. 10 million years means that particular star we consider is a G series star, that our sun also belongs to that series particularly. Few stars are much more longer life. So let us come to that particular star. Our star is sun. Look, in a galaxy there is a two kind of star. One is a single star. Okay. So there is particular two kind of stars. One is a single stars like sun, and there is a binary stars. That means there are two stars very close to each other. What happened? The binary star actually developed the photostars from each other, and one member of this form can influence the companion. These are the photostars. And what happens? If one of the member is giant star, it lives behind the neutron star or black holes and X-ray binding can form. But a matter pulled from the stellar structure, subcontinent get extremely hot, nearly around 10,000, 1 million degree Fahrenheit. Now, few things about solar about the sun. As I said, that sun is gaseous. Sun is actually gas, not solid. So you will find there is some kind of axial rotation of the different type of axial rotation of the sun. At center, it's nearly at center it's a 25 days, Earth days. Actually, it's defined by Earth days. I mean 24 hours. So at equatorial regions, the sun's rotation is 25 Earth days, whereas polar region it's a 36 days. And sun also tilt with a 7.25 degree. That is actually the, if you consider the axis of the sun. What happened, you know, that sun have some kind of periodic cycles. One is sun solar activity cycles, another is the solar magnetic cycles. In that case, solar magnetic cycles, it was been observed that sometimes sun tilts its poles. I mean magnetic poles, south poles and north poles. Now, the sun formed 4.6 billion years ago in a giant spinning cloud of gas and dust called solar nebula. And nebula collapsed under its own gravity and spun faster and flattened the disk into disks. Most of the nebula matter was pulled toward the center to form our sun, which accounts for 99.8% of our solar system mass. Much of the remaining materials from planets and other objects that now orbit the sun. Our solar system is moving with an average velocity of 4,50,000 miles per hour. But within this speed, sun will take 230 million years to complete its orbit along with its galaxy, round trip along with its galaxy. Now, if we talk about, although we said that the sun is gaseous ball actually, but still at center of the sun, density is huge. I mean, it's more than 19 times or more than of gold. And here are three particular regions. One is the radiative region, there will be convective region and photosphere. But the secret over here that due to hydrogen helium fusion, the energy coming out from the core cannot able to penetrate the radiative regions easily. So the part of sun, the temperature drop. Let me come out to here. Okay, so the regions, as I said, that convective zones, the radiation bounce around the radiative zone and taking 1,70,000 years to get from the core to the top of the convective zones. That the things I want to say here, the energy from the core is carried outwards by radiation, but still the radiation cannot be coming out easily from the core. From the radiative zone, it's again bounce back to the center. Then after it will come out, and it will take around 1,70,000 years to come out from the center of the core to the convective zones. So at the beginning I said, one Japanese scientist who has done huge research on astronomical instruments, which are ancient astronomical instruments, which were used in before AD, I told, a century, 5 to 12 century AD. And he has said that Siddhantas, that was Bhaskaracharya written books, Basquiat 1 and Basquiat 2 actually written huge about the astronomical instruments. What numbers of instruments that the scientists used are mentioned. And there is a two particular part of that Siddhanta. One is the Graha Ganika Adhyay, another one is the Gola Adhyay. Gola Adhyay that actually talk about the sphere. So look, our ancient scientists already knew about that sun or earth or the planets are sphere. It was not that the only European scientists has been said this one, but because these ones are Indian scientists already knew this matter, and they expressed that they have written all these things on that particular syllabus. I'm not talking about the syllabus right now here, but if you are interested to see that particular paper is available on the websites. It's a 125 or 160 page, around two papers you will find on Watson. But we cannot forget the contribution of the European scientists in astronomy. If we look back over this one, then ancient, it's not ancient actually, it is from the Renaissance, at the time of Renaissance, European Renaissance. We will find there is a huge number of, many modern instruments, nearly modern instruments that is starting from the Galileo 16th century. Earlier than the astrolabe, arbitrary sphere quadrants, which are even used to observe our galaxy, to observe the sun, constellations, stars. Now let me say about some activity cycle. As I said at the beginning, that solar cycle, there is a two particular cycles of the sun we have seen. One is solar cycle, that 11 years. Solar cycles, it actually determined or it actually identified by this year that 2024 is the important year in solar astronomy because the maximum sunspots can be observed here this year. The sunspot sometimes erupt into powerful solar storm that shoots streams of the charged particle into space, occasionally in direction of the Earth. It's not mandatory that the sun only shoots the eruptions towards the sun, toward the Earth. It also erupts the storms towards other planets also. But from Earth we can observe particular source. There are some powerful storms that can bombard the Earth magnetically, disrupt the power grid and knock out our satellite in orbit about the planet. And probably that was the main reason that solar effects on climate dynamics. And as we are finding that this year even the climates are coming little bit late. Winter, summer, if we observe that summer is longer, definitely there is one reason of global warming. But we cannot ignore the effect of solar storm or sunspot number. That solar cycles, even having I want to make that the solar cycle have a great role to influence the solar Earth's climates. That we cannot ignore. Okay. Here I put a video of how the hydrogen helium, actually how the helium hydrogen fusion happens and how the energy radiation coming out from that reaction.
At the first step of the proton-proton chain, two hydrogen nuclei. At the first step of the proton-proton chain, two hydrogen nuclei collide to produce deuterium, which is a with a proton and a neutron. In this reaction, a positron and a neutrino are emitted.
Here, that neutrino actually come out, and look, this is almost 100 years problem, missing particle theory. actually for what Beckers has published numbers of papers, and finally it was solved, and another particle, that particular particle is found is a neutrino. Earlier that equations, the neutrino was not considered because neutrino is a small particle, smaller, I mean it's one of the smaller particle even of atom or electrons, and it can even penetrate Earth. So this is very difficult to consider in consideration at the beginning of the astronomical physics, astrophysics. But later on, when they are going to balance the equation, they found that a particular energy are going to come out of that equations, and that is neutrino. So it was become a challenge that time how the neutrino will be detected, because the energy is actually says that the particle is very small in size and it's a huge energy, it even can penetrate the Earth. So we can detect easily beta radiations, gamma radiations, we can detect alpha particles also. But about the neutrino, it's very difficult because its penetration is huge, penetration power is huge. That time, one scientist came out, and his name is Professor Raymond Davis. He is an electrical engineer. He was an electrical engineer, and he developed a particular experimental setup to detect the neutrino particles, and got Nobel in 2002.
At the first step of the proton-proton chain, two hydrogen nuclei collide to produce deuterium, which is a nucleus with both a proton and a neutron. In this reaction, a positron and a neutrino are emitted. The positron annihilates with an electron, and gamma rays are emitted. The neutrino escapes the sun. Meanwhile, a third hydrogen nucleus collides with a deuterium nucleus to produce helium-3. A gamma ray is emitted in this reaction. Two helium-3 nuclei produced in this manner will collide. In this final collision, two hydrogen nuclei are released, and a helium-4 nucleus results. The net reaction turns 6 hydrogen nuclei into 2 neutrinos, 6 gamma rays, and a helium nucleus. 2 hydrogen nuclei return to the gas, and may go on to participate in another reaction.
Okay. This was the basic solar physics happens in the core of the sun. Now, as an instrument engineer or electronics engineer, how can I detect that? How can I understand that particular chemical reaction sitting on Earth? How? By detecting the radiations. That means the gamma radiations. So that's when we have to develop a telescope which easily recognizes the gamma radiations as well as the helium abundance. So that particular way, that was a particular responsibility for those engineers who have developed that telescopes. And this way, the engineer, we actually not only build instruments for industrial purpose, we develop some instruments for some kind of research, which give us the immense knowledge about the universe. Not only universe, we can even interpret of the solar, climate physics or climate, geoclimate or geophysics. We'll discuss that kind of gamma telescope later on.
At the first step.
So as I talked about the abundances, so we said about that the sun actually sun mostly is a hydrogen helium ball, but it's not like that. There is a certain percentage, maybe within 2% definitely, but within that there is some other particle also been observed. The particles elements are mainly lithium, beryllium, boron, carbon, nitrogen, and oxygen over here. And look, they are how they are recognized depending on what we know that there are emissions, spectroscopy or in a telescope. Those are will help us to identify what kind of element analysis happens. Except this one means except this kind of instrument to exhibit spectroscopy or what I said that gamma telescope, we will depend on some other parameter to define the solar dynamics. The other parameters, some are here like sunspot number that easily observed by optical telescope, solar flare that it can observe by telescope, total solar radiance that can be observed by that can be measured by pyranometer, and that pyranometer might be ground-based, might be ground-based pyranometer definitely having certain kind of error because the absorptions of the solar radiations in atmosphere is 70% around. So it's carrying very small information about the sun if it will be installed on Earth. But if we can install that pyranometer or pyranometer like devices on satellite or space flight, then definitely it can give us immense information about the sun dynamics or solar dynamics. Coronal mass ejection, that also another parameter that actually detects the number of coronal mass ejections happens over the sun surface, particular surface toward the Earth, and detecting the number of coronal mass ejections and their strength. We can even interpret the magnetic cycles or magnetic magnetohydrodynamics of the sun. Need to know flux, that actually very important finding in end of the 20th century. And J network here, solar wind, that is a green parameter to decide on solar magnetic field. Solar filament, that also gives us information about some kind of abundances that actually we want to observe, and even the gamma radiations detectors. Explosive events, X-ray bright points, and some electromagnetic radiations. So I actually stated the type of instrument here to three types. Actually, we consider that one is the energy particle detection. Energy particle detection means mainly of materials and spectrals who are analytical instruments. That's those kind of instruments actually installed in space flights. And there's a two-way. One is the absorption spectroscopy, definitely that absorption and emission spectroscopy that definitely give information about the particular radiations, which will say about the source. And not only that, there is a time to flight methods that actually give us the particle size and mass and information about the particle. So, if we talk about the energy particle detection, this is a one kind of devices or one kind of instruments installed in space flights to detect the energy particles that are coming out from the suns. Not only coming out from the suns, in fact, following units. One is suprathermal electrons and protons. That is states suprathermal electron and proton. Another one is the electron proton telescope. Electron proton telescope is having a collimator, and through what the electrons will be allowed, and time to time methods will be main methods that will actually detect, and definitely there is a solid state detectors that will recognize the energy particles. And suprathermal ion spectrograph, that is CIS, that's also important one, and in high energy telescope and instrument on the units. This is particular device actually installed in satellites to detect the particular energy particles. Like suprathermal electron proton sensor, the sensor is designed to measure the proton and electron at suprathermal energy. For this purpose, they employ principles and technologies used for previously on the board space-borne instrument. Basic detector is co-aligned sensor heads with a parallel field of view. One of the sensor heads contains permanent magnet. The permanent magnet actually gives us a magnet channel. Another one to detect for electrons is called integrated channels. that were elliptical channels that was discussed in the next part. And that two part actually help us to detect one proton, another one respectively electrons. To measure the kinetic energy of the particle, each sensor it contains solid state detector, that I say. Calibration of this particular instrument very important, because we know these are the very sophisticated instrument. Although we have seen the mass spectroscopy or any kind of analytical instrument is big in size, but these are actually payload of satellites or space. So they are designed in small area, very compact area. So these are sophisticated. At the same time, it was very much it was a big challenge for the instrument engineer to design that instrument which will be installed in a very small area, and it should be light-weighted as if that rocket can peer. The calibration purpose of step unit was operated in the thermal vacuum chamber with mission plausible thermal gradient occurring barium isotope, specifically focusing on low energy gamma rays. There is another instrument that probably used for the calibration of particular that device is called Faraday curve. I'll talk about the Faraday curve later on. The calibration of each channel was found to vary with temperature, with acquiring data, linear dependency of the calibration parameter on the temperature. The seas we can see over the pictures here. This is the path that energy particle will require to traverse, and the time will be measured. This is small mass spectroscopic devices, you may say. That is suprathermal ion spectrometer is a smart spectrometers that measure the energy, velocity and composition of suprathermal particle from helium to iron, with energy ranging from just above the solar wind to mega electron volt per nucleon. It also determines how long it takes for the particle to pass through the instrument. It is used to time to flight spectroscopy to measure the time of flights and residual energy of the ions. This instrument has two parts. One is SIS A and SIS B. SIS studies the superthermal particle created in solar flare, coronal mass ejection and shock in solar winds. So we know about the solid state detector. It's almost same like a solar sensor or photovoltaic sensor, but little bit sophisticated here. Like silicon diode detectors that are fabricated using 200 angstrom thick phosphorus doped polysilicon layer that probably not given over commonly available solar cells. And 220 angstrom thick aluminium layer is deposited on the top of the polysilicon, as if that is aluminium layer easily penetrated by energy particle and will be detected by the solid state materials later on. And single pixels are arranged in an array of 3 rows and 5 columns. If I talk about the telescope, there is a two kind of telescope. One is the energy particles telescope, another one is the optical telescope. So, to know about the optical telescope, we come across the Galilean telescope, Newtonian telescope in class 8 standard physics books. So I don't want to discuss this one here because we are very much aware of this technology also. Newtonian telescope is almost similar like refractive telescope, reflective telescopes. So even I am skipping that particular optical telescope here. I want to talk about the neutrino telescope, energy particle telescope that actually detects some energy particle which having immense information about the sun, which is not easily detected by the optical telescope. Because why we can use the optical telescope? First, when we are going to say about image processing of the sun, that is also very important because in India, Indian Institute of Astrophysics, they are actually doing some research. They installed an optical telescope there for 110 years, old optical telescope there, which detecting the sunspot, not only sunspot, solar flare and coronal mass ejection. They take all images from that telescope using different type of filter, helium filter, potassium filter, and this kind of filter actually help us to recognize a particular radiations. And then radiations will be analyzed. That is actually called solar spectrum. From the solar spectrum, they can interpret about the solar dynamics. But these are very old old instrument, but then definitely it gives some relevant information about the solar dynamics. But like energy particle telescope, which gives us the like helium, hydrogen abundance, or iron abundance, or elemental abundances, information of the elemental abundances. So we need to know a little bit about the neutrino telescope and gamma ray telescope and radio telescope. Neutrino telescope, that I said that Raymond Davis Jr. he got Nobel for this ones. He developed an experimental setup with using deuterium. Heavy water swimming pool to detect the and all the experiment to detect the neutrino flux or neutrino actually underground. Underground means it was installed in mines. Even India is trying to install a neutrino flux neutrino detectors. It's nearly 1.2 kilometers below the below from Earth's surface, and they are trying to install that device near South India. And it called near Bangalore, Gauri control. But what is neutrino, as I said, is a nearly massless, electrically neutral, chargeless elemental particles. Neutrino are very hard to detect due to their non-interactive natures. And neutrino can penetrate hundreds of meters of rocks. Neutrino, on the other hand, can go through the entire planet without being absorbed, and it is named also ghost particle. And this is ice cube lab, where we will find the ice cube used with some kind of gallium, with some chlorine-rich solutions. Chlorine-rich solution means actually chlorine-rich means it's not a normal chlorine. The isotope of chlorine are considered here. And what happened? Like I said that at the first detection of the neutrino actually went out by a swimming pool of heavy water. Heavy water means we know there will be a isotope of hydrogen also. Okay. Right. Heavy water body H2O. Can I remember? It was said by H2O plus, no? Plus, sorry. So, like here also, the ice cube neutrino laboratory, where we will find that the chlorine-rich solution used, that chlorine are definitely isotope of the chlorine are considered, and also we will find that gallium, germanium conversion are used. Later on, that chlorine-rich isotope, when it collide with the particular isotope collide with the neutrino, it produces argon gas. So the percentage of argon gas is collected by electrodes, sensors, and then after this is that how much neutrino have been collided with the chlorine isotope. Another telescope is the Fermi Gamma Ray Space Telescope, and I know that as we come across that equations that they are saying that the two hydrogen atoms collide and forms helium ions finally and radiate gamma. The neutrino which coming out from the reactions heating with the positons produce the gamma radiations. That gamma radiation required to be detected, otherwise you cannot say about that particular reactions. So the gamma telescope give us that particular information. I mean, otherwise we can say that the engineer who developed the gamma telescope actually able to solve the missing particle theory that was probably 100 years long mystery in the astronomy. The Fermi Gamma Ray Space Telescope is a high energy gamma ray missions that studied that studies the highest energy particle accelerator in nature. With Fermi, the astronomer at long last has a superior tool to study how black holes rotate from cooling matters in and can accelerate jet gas outward at fantastic speed. Fermi carry two instruments. One is a large area telescope. This one is a large area telescope. And there will be another GBM. gamma burst monitoring instrument, GBM. Another is that particular part of this gamma radiation, gamma ray space telescope. Another is the Cherenkov telescope. Probably we are very much familiar with the Cherenkov radiations. When energy particles hits with the detector, it's rated a blue light. Depending on the blue light, that blue light detections actually done by that Cherenkov or Cherenkov telescopes. That it's detected the particles are released from the gamma radiations with a few tens of gigaelectron volts in that particular radiation, cosmic radiations. And there is some kind of decrease in cosmic radiation. Later on, it was named on that particular scientist is called Pulse decrease. So the cosmic radiation detections are, in other words, can say about help us to know about the solar periodical behaviors. Solar particle detection that already been discussed. Plasma instrument. This instrument measures the property of charged particles that make solar winds and other space plasma and temperature, density, velocity. Magnetometer. Instrument measures the strength and direction of the magnetic field in the space. Dust detector. Dust detector means when we say about generally when we say about the star, there will be nebula. Even from the nebula, the star formation happens, or when star newly formed, there will be a build-up. There will be disks. In the disks, there will be plasma and dust particle, or definitely. And look, the scientists installed an instrument not for particular detections. It was installed an instrument to observe a phenomenon. That phenomena might be 20 years, 70 years, or 100 years long, or more of that. So the instrument once installed will give us the information. Might be one information, but that is not sufficient to interpret about the star formations. So it was need a sequential observations. So when we are going for sequential observations, we have to find out what is the role of the dust or the leaks or around it. Like we know that one of the planet having a leaks. Can you say that? Which planet will have a leaks? Saturn. So good. Saturn having leaks. So can I ignore that leaks? Why is that Saturn having that leaks, whereas Earth having no leaks, or Mars no leaks there also? So that is a very interesting fact of the Saturn. Okay, Saturn having a huge rotation speed. Huge rotation speed for what? The blast come out from the planet and from that particular. So it is not happened for other planets. So this way we can interpret about the star region where the leaks was being formed, and whether the leaks later on going to be a small planet, and even that in those planets is there any chance to be new Earth? So this kind of observations are actually the objective of the astronomer. So the dust detection is the important part of in their research. Charged particles detectors. So the instrument important, as I said, that it is give us a complete understanding of the space environment and the effect of the solar activity on Earth atmosphere even, and protect the spacecraft.
The heavy ion sensor will be taking samples of the solar wind, which will help us learn a lot more about the sun. My job is to find the characterization of the real instrument so that we can understand the configuration of the instrument no matter what region of space it's in and no matter what configuration the instrument is in. Here we have a view of a computer simulated model of the instrument as well as a schematic model of the instrument. A particle will enter the instrument through the entrance aperture. It's then guided by the deflectors and the charged electrostatic analyzer plates. If it makes it through the electrostatic analyzer, then we know that it has a specific energy per charge. At that point, the particle is given a post-acceleration voltage, which makes it easier to detect. It passes through the carbon foil, where it becomes neutral, but kicks off a secondary electron. The secondary electron is guided to the start signal, while the neutral particle continues to the solid-state energy detector, giving us an energy reading. When the neutral particle strikes the solid-state energy detector, it kicks off another secondary electron, and that that secondary electron is guided to the stop signal, which gives us the time of flight of the particle through the time of flight chamber.
This secondary important is very important. It sometimes creates some error in
About the
detectors.
plasma in space. So wherever the instrument is at a given time, we can characterize the distribution of the plasma in space. As we're collecting the data, we're able to send them back to ground stations where they're aggregated, checked over, and then we use them for science.
So, particular the phase flight particle instruments, that is important to give the proper information about the solar dynamics or any stellar structure. But as I said that the secondary electron emission is sometimes create some problems. We will consider these things in future also when we are going to say about some instruments. So mostly the instrument having a same block diagrams, the collimators, ionizer, and then after the energy analyzer, mass analyzer, detectors. And then after the analog processing, the signal processing, this part are we already familiar. So neutral particles instrument, only there is an ionization element to convert the neutral into ions. So like we said the neutrino is a neutral particle. Similarly, there is any kind of particles that come towards Earth, but very much neutral. What we have to do to detect this one, we have to make an ionization chamber to ionize the neutral particle. Then after we have to detect the ions. And the second analyzer section that performs ion mass discrimination. The particle encounter a detector that converts the arrival of the particle into an electrical signal that can be further processed in the signal processing. This part is the actual diagram of the time to flight methods of mass analyzers, and we are very much familiar with this one because we used to teach analytical instrument. Another important device that we actually found in ground-based instrumentation, so ground-based space radiation detection instrument is a multiplier tube, photomultiplier tube. There is a two kind of photomultiplier tube and actually used. One is a discrete photomultiplier tube, another one is a continuous photomultiplier tube. Probably whatever we used to teach our student is a photomultiplier tubes that mainly a discrete photomultiplier tube with a diode. Coming to that point later, let me say about the error, source of error. So, source of error in uncertainty is measurement and derive the physical quantity are numerous. If the goal is to compute the fluxes and distribution function, the uncertainty comes out from geometric factors, detector efficiency, analyzer voltage, and outbound response, and solar UV spectrum. That is another important parameter. This is the sensitivity of the solar UV. So later on, the UV telescope, ultraviolet radiation detection telescope, also been in space flight to detect this part, and it was used to remove after the measurement of energy particle or any other kind of radiations. That is one instrument in space flight used for energy particle. It's like a deadweight tester. In our systems, deadweight tester is a calibrator. Mainly used for calibration. Similarly, the Faraday curve is a current transducer or current instrument detect the current after detection of energy particles. Create of currents that actually detected by the Faraday curve after energy particle detections. The measurement accuracy of Faraday curve is affected by the series of secondary processes created by the particle impacting on the curve, such as emission of secondary electrons. That I told you that video when we are going to observe when we observe that video, we have seen that the secondary electron emission happens and it's coming out from that curve. That secondary electron emission of electrons creates some kind of disturbance accuracy. Faraday curve are well suited for absolute current measurement because they are not affected by same gain degradation as channel electrons multiplier or multi-channel electron multiplier. Double focusing mass spectrometer includes the Faraday curve in the instrument detector system. This is a continuous electron multiplier. With that continuous electron multiplier having a uniform electrodes, high resistive electrodes. High resistive electrodes. What happens is when once electron is hit on the particular surface, then it gets numbers of electrons and detected at the end. This is one important device used, but it was very old instrument in space radiation detectors. This is a discrete electron multiplier that we used to teach our students. The photomultiplier where the numbers of diodes are used to detect the bombardment of electrons. X-ray spectrometers. That I said that the gamma radiation, later on the gamma radiation get even X-ray. That equation already been discussed. But that gamma X-ray spectrometers give us the information of X-ray spectrum, solar X-ray spectrums and solar X-ray burst. So that kind of radiation giving us information of what kind of model we are going for this year. Like as I said that the sunspot number will be maximum 274. So it will be a headache for the scientists that what is going to happen in solar climates. So they want to develop a model to predict a forecast about the climate change and what should be the protection, what should be the measures should be taken by the government to make a good policy for the civilian. So to detect this kind of, to say that kind of prediction or to make some kind of forecasting model, what we have to do, we have to detect the radiation clearly. The X-ray spectrometer is also give us that kind of information to give us a good model on that particular events. Events when the phenomena happens in the phenomena happens inside the sun's core as well as on the climate or in the climate of the Earth. There is some other instrument. I am not talking about this ones. Let me say about some solar eruptive events. And this is the normal solar flare. Solar come out from the solar gravitational field. So what happened? It's again fall on the surface of the sun. So that is actually the reason of the magnetic connection. Magnetic connection, it was said the magnetic reconnection because once it will be coming out from the surface, then again the magnetic connection happens. So that's why it was called reconnection. Standard model of the solar eruptive event. This kind of model actually give us help on the research. Now, what we used to do when the radiation spectroscopy give us some kind of spectrogram, we have to do some kind of analysis. Analysis means what kind of material element abundance happens, what kind of phenomenon is going to happen. So in that case, there will be three kinds of spectrum we used to observe. One is the continuous spectrum, second is the emission spectrum, third one is the absorption spectrum. Continuous spectrum produced by incandescent solids or gas at high pressure. Emission spectrum can be produced by a gas at a low pressure, excited by heat or by collision of electron. Absorption spectrum happens through cooler gas consist of series of dark lines characteristic composition of the gases. This is one model of the solar flare. It's the image of the solar flare and how the model actually useful for the solar research. Look over here that the flare coming out, but this whole thing is a filter by X-ray filter and the image actually taking X-ray image. So the radiation is the X-ray radiation and that X-ray radiation will say that what will be the hard X-ray source. Once that will be hard X-ray source and this might be the reaction or the hydrogen helium conversion reaction is strong, so strong here that if this kind of reactions happen, the surface facing toward the Earth, definitely it is going to affect the environment, the Earth's environment. This part is optical telescope, but I am not going to discuss this one here. Now let's come to us the solar data analysis. Solar data analysis mainly two kinds. There is a time series analysis. Another one is a composition analysis. I am not talking about the composition analysis because that image processing part actually do this one. The earlier spectrum is Vernier spectrum, emission spectrum, emission spectrum or absorption spectrum actually give us that kind of analysis. Later on, there is another part is the solar data analysis, mainly concentrated on the time series analysis. In case of time series analysis, if some events happens, the process will be monitored for long time, like sunspot number variation. The sunspot actually monitored from 250 years back. It's monitored from 250 years in around 17th century. It's been observing. It has been observed. Another thing is that the solar irradiance even. Solar irradiance or total solar irradiance even measured for around 70 or 80 years. So this kind of measurement is not a short time process, it's a long time process. So the data we are going to consider is a billions of data. So it's a part of big data analysis event, we can say, but it's definitely concentrated on the time series analysis. Why? The trend, seasonality, periodicity, or spectral density, these are the very common term for DSP. We have studied DSP, so we know that power spectrum density, and some mathematical part is the chaos and irregularity what we study. Chaos and irregularity give us the information whether this particular process depends on its previous state or not. If it depends on the previous state, then we have to check out that the data is saying that is that periodic or aperiodic. If it is periodic, then we have to check out whether it's a multi-periodic or not. So this way we can enter the details of the analysis. So to know this one, first we have to go for the trend analysis, second one is the seasonality analysis, third one cyclicity, the irregularity. These are the sequential investigation we have to do for time series analysis. Later on we have to go for the periodicity analysis. After periodicity analysis, we again go for some kind of statistical analysis that will be mainly confidence analysis. So whole model will be stochastic model. It is not possible to get the deterministic model, but the stochastic model even can give us a good information about the process. And depending on this model, we can even forecast or predict the phenomena, and we can take the required measurement to sustain the change of the environment. So these are the main issue or objective for time series analysis. One is the building a model that represents time series, validating the proposed model, and using the model to predict the future value and improve the missions. In a time series, we normally ask the basic three questions here. Is it stationary? Is there seasonality? Is the target variable autocorrelated? Look, the last one, is the target variable autocorrelated? Up to that one we probably know. Last day probably a question was here. He has given you information of the Granger causality, and that mathematical operation even helps us to know whether that is the reason or the cause. So that means when two events will be analyzed, then Granger causality give us that which will be the reason, which one is the reason. So this event considered in the time series analysis. In time series model, the oldest model is auto-regressive model. Later on, it was auto-regressive integrated moving average model and auto-regressive moving average model. And finally, after the machine learning development, and definitely depending on this kind of auto-regressive model or auto-regressive moving average model, we can able to forecast. But the accuracy of the forecasting is not so accurate. Later on, after invention of machine learning and artificial intelligence, the LSTM gives us a good results. LSTM is a part of RNN, recurrent neural network. Probably you all are familiar with this one. And LSTM is a long short-term memory methods. And this method helps us to give us a great, heavy, accurate, much more accurate than the ARIMA or ARMA methods to forecast some events. Except this one, there are some kind of methods that is autoregressive method also. Exponential modeling, double exponential modeling, triple exponential modeling are used to model some solar events. In case of autoregressive models, we know that the input signals depend on some previous state, or the output that might be the yk output which depend on the previous state yk minus 1. That this is the basic block diagram of autoregressive model. In case of solar model, when we are going to design theoretically, we have to go for a long term, higher order of autoregressive model to detect this one. And the diagram is a little bit familiar, we have seen previously. Moving average model, that is the moving average model, they are combined to reduce the noise, reduce the noise in other words, for forecasting of predictions. This one is the autoregressive forecasting of a sunspot number. These are the solar cycles. Solar cycle 1966 to 1976. It's not a 10 years, it's 11 years. But we cannot say that solar cycle, solar activity cycle always follow 11 years. It's a little bit difficult to predict that it will be 11 years every time. Although it is periodic, but sometimes it was observed in 8 years is the solar cycle. Sometimes it is observed that 14 years will be the solar cycle. Normally it is 11 years, while 4.5 years is 4.5 years means solar minima to maxima, and 5.5 is for maxima to, 6.5 is the maxima to minimum. But in that case, it is the prediction of the solar cycles, sunspot number. The sunspot number is observed. These are the solar cycle according to what the sunspot number have been seen. And the red line is the ARIMA method, which actually predicted data, or it was found that almost accurate. And the long short-term memory, that is LSTM method, is a very familiar. I think it is familiar to you all. It's a part of deep learning. It's come out from RNN, the recurrent neural network, and it gives us a much more better result in customer predictions. This is the age function which actually modified to predict the new value, and this is modified with two functions, tanh and sigmoidal functions. If you go to this LSTM model, you can even say any other type of time series can be predicted by this model. And what is the best advantage of LSTM is today, ChatGPT. The ChatGPT actually developed on LSTM. So it is modified version of RNA, and that's all about my lectures. Thank you all. I'm in time for it. It's very boring, I know, because it's purely some separate zone of research or discussions. This is astronomy, which is not related to the instrumentation or electronics communication. Few people having interest to know about some kind of astronomy, they probably get a little bit help from here. So anything want to know more? Thank you. Stop this one.
Participants, if you have any question, please share your thoughts. Offered an insightful insightful exploration of the tools, methods and advancement in the study of the sun and its phenomena. Beginning with the fundamental principles of the sun and the standard solar model, the discussion highlighted key solar phenomenologies, the solar cycle, sunspots number, solar flares, coronal mass ejections, and the historical evolution of astronomical instruments. Professor Patro delved into the functionality and application of modern instruments such as telescopes, spectrometers, step unit, cosmic ray detector, and particle detectors, as well as innovative techniques for solar data processing. The talk emphasized the significance of time series analysis in understanding solar activity and predicting its impacts. The session concluded with the reflection on the synergy between ancient particle practices and innovative technology in advancing solar astronomy. The presentation also touched upon data analysis techniques, particularly time series analysis, used to interpret solar activity patterns. Emphasis was placed on the integration of computational models like ARIMA and LSTM to forecast solar phenomena and improve predictive accuracy. So this session was both informative and inspiring for us. So now, before we move on to the next part of our program, I would like to take a moment to thank our speaker once again for his time and expertise. We would like to express our gratitude to Professor Patro for his enriching sessions. So to do so, I would like to invite Dr. Somo Roy, Associate Professor of AI Department and also the coordinator of this FDP, and Dr. Roy is also the direct student of Professor Patro. So to present the token of appreciation to Professor Patro. I again request Dr. Roy to present the memento to our esteemed speaker as a symbol of our thanks for his valuable time and the knowledge he has shared with us. Professor Patro, we are truly honored by your presence today. Thank you, sir. Before concluding, participants, I would like to remind you all about the industry visit to Haldia Energy Limited. Transportation has been arranged and we will commence our journey just immediately after the lunch. So to ensure a smooth and safe experience, please carry your Aadhaar card or voter ID card and also ensure to wear a covered shoes for safety issues. So we look forward to your active participation in this industry visit. So before that, with this note, in that industry visit also wear the I card of this FDP. So